Good morning and welcome to lesson 12 of this course on PID control. Now, we will look at a phenomenon, another problem which occurs typically with integral control, and that happens when you have auto manual transfer. Now, let me first explain this term. There are many, most processes will also allow the operator to give input, that is, if he wants, then in certain situations you can bypass the automatic controller and rather using some input device like a potentiometer or a knob or a switch, you can give manual input to the plant and you can slowly build it up, and then maybe for some purpose, right, or and then but then finally you do not want to run the plant manually all the time. So, you want to switch over to the automatic control. Now, during this switch over, problems can occur, as we will see here. So, here is a case where so you see that this is the process, this is the actuator, and the input to the actuator can come either from the automated PID controller. So, this is automatic controller, and this is manual. So, the operator is actually giving some input here, and here is a switch, here is the switch which you can flick, so that the actuator gets its input either from the PID controller or from the manual controller, correct. Now, imagine now the main question is that when I am transferring, how do I know? For example, suppose here the input was, let us say, 1 volt. Now, how do I know that when I flick this switch to auto, I shall also hear the input existing maybe 10 volt. So, now what will happen? That previously the actuator was in 1 volt, was getting an input of 1 volt. Now, from 1 volt suddenly a 10 volt output will go to the actuator. So, the actuator, if it is a motor or if it is a valve, it might get a shock. Similarly, the process also will get a will tend to get very high inputs. So, this shock, that is, we normally try to operate the processes so that if we want to increase the input, we ramp it up gradually. You do not give an input 1 volt now, 10 volt, then again minus 2 volts. So, such inputs are sometimes detrimental to the equipment either in the process or to the actuator equipment. So, the question is how to ensure that the PID output is close to the manual during transfer. In fact, it often is not, because of the fact that the PID control, remember that its output is not going to the actuator, but it is all the time getting both the set point and the measurement. So, it is all the time computing the error, computing its integral, everything it is doing. So, it is quite likely that the PID control output is actually saturated during the time that you are manipulating the process with manual control. It is quite possible that the PID output has got saturated, it is stuck either at its negative maximum or its positive maximum. So, now if you suddenly flick the switch over, you are likely to give the plant a shock, and we want to avoid that. So, how do you avoid that? So, for avoiding that, for avoiding that, we, rather than giving the input u, we would like to give the input delta u. So, you see that this is a clever scheme which avoids that process. So, suppose you are in manual control. So, you are every time you are actually giving delta u. So, you are, maybe there is a plus minus switch and you are flicking the switch to plus. So, the input is going up, every time you are giving positive delta u. If the flicking the switch to minus, you are giving negative delta u, and these delta u's are getting integrated here by some device, okay, maybe in the actuator. Now, and the PID controller is also does not give you u, but does give you incremental input delta u. Every time it computes delta u. How it computes delta u, we will see very soon. But suppose the PID control is implemented in a form which is known as the incremental PID form, and it gives you delta u, right. So, now now what is going to happen? Now, suppose up to UK minus 1 you were in manual. Now, suddenly in UK, just between UK minus 1 to K, between the time instance K minus 1 to K, you have flicked the switch to auto. So, what will happen is that now a UK minus 1 plus delta UK term will be added to the actuator, and this will come from auto. This will come from the auto mode. But you see that this is actually a delta term. So, it is an increment. So, it cannot be very large. So, the process will get the old manual input plus a little change which is due to auto. So, it will not get a shock. So, gradually these delta UKs will build up and will slowly take the process from one input to another input. So, the transfer from auto to manual mode is going to be bumpless. That is the terminology which is used. Okay. So, these are some problems which you need to take care of when you are trying to implement, especially when you are trying to implement integral terms. Now, let us come to the derivative term. So, let us look at the first problem with derivatives, that is that derivatives typically tend to blow up high frequency noise. And where does high frequency noise come from? High frequency noise comes from sensors amongst one things. For example, typically let us consider some a flow sensor. Flow sensor, flow is always turbulent. So, for the fluid actually flows in random fashions. Whenever you have a flow beyond a certain velocity, flow is turbulent. So, whatever sensor now the turbulence induces frequencies which are much higher than the average volumetric flow rate. So, while the average volumetric flow rate may be varying like this, the signal that you will get from the sensor may induce very high frequency components. So, these signals are actually due to the turbulence. So, this gives a noise, right. Now, the point is that if you take this signal and if you consider the case that you have this point needs to be understood. Suppose you have a signal which goes like this, and on this you have a noise. I am drawing, actually noise will be much more higher frequency. Now, if you take derivative of this signal, what will happen? The derivative of the low frequency original signal will remain positive up to this point, will slowly fall and then will become negative here. No, the derivative around this is going to be positive, then will fall to 0 and then become negative. What happens to the derivative of the other signal? See, the derivative of the other signal is going to start from positive, within this short time it will reach a negative maximum and then it will again. So, it will be widely varying. So, you see that while these signals are more or less close to each other, their derivative terms are completely different. So, if you calculate a derivative, exact pure derivative, then even a small amount of high frequency noise is going to give you a lot of difference in the control input. So, therefore, you need to use a derivative which will act like a derivative up to a certain frequency, but beyond a certain frequency its gain will not blow up, right. So, we need to limit the gain for high frequency noise. So, to do that, we simply, the transfer function of a derivative is S. If we now consider the transfer function of the signal S by 1 plus Ts, imagine, this I need to select the pen. So, that what is the gain of the, so as S varies, that is as the frequency varies, S by 1 plus Ts will, at low frequencies this term is small compared to 1. So, it acts like I don't know. Okay, so it it acts like S in this part of the region, while in this part of the region where S is large, then it acts like this, then it Ts is much greater than 1, and therefore this gain becomes equal to 1 by T. So, this level is 1 by T. So, you see that we have in the lower frequency region we are having a derivative, but in the higher frequency region we are having a constant gain of 1 by T. So, that is what, so that is how you need to realize your derivative. So, the idea is that for low frequency it is S, for high frequency it is 1 by T. Now, this is also useful for certain kinds of mechanical actuators, as I said, that if you give a very high frequency signal and then creates derivative, then you are going to give it very high frequency positive and negative torques, which is not good for a mechanical actuator like a control valve. It might damage the valve, and as I have given an example that such noise may come from various kinds of measurements, especially flow measurements, which are very common in an industrial process. So, now we come to the, now there is a second problem associated with the derivative control structure, and so far as we have seen, we have implemented the PID control like this, that is the error term, this is the error term. The error term goes here, gets multiplied by Kp, gets multiplied by Ki, and gets multiplied by Kd also. Now, as we have seen that we want to avoid giving shocks to the process, right. So, what happens when you, in many cases the set point is changed like a step. So, if you change the step, what is going to happen to the error? It is also going to change like a step. So, then what will happen to the derivative output here? It is going to be at this time is going to rise very much and then it is going to fall to 0. So, you are going to give a shocking input to the plant if you put the derivative here. So, now the question is that how can I avoid such shocks, but if R is not changed, if when R is constant, if there is if Y changes due to various other factors like disturbances, I need to keep the derivative control. I do not want to sacrifice derivative control, I want to have it except for the instance where R changes like a step. So, a clever way of doing that is by realizing that when R is constant, dE by R is equal to, or rather E is equal to R minus Y. So, dE by dt is equal to, when R is constant, it is minus of dy by dt. So, rather than having d by dt here, I can also take y here and then change the sign and implement the same block here. So, when R is not changing, I am going to get the same effect as dE by dt, but when R goes through a step, there is absolutely no effect here. So, during that time it will simply slowly rise, and I mean corresponding effect you will get as y rises, you will again get the PD effect, but this shock will not come. So, this is something which is to be remembered when a derivative control is to be implemented. Now, we come to the last topic, that is the digital realizations, because nowadays most controllers are actually implemented using microprocessors. So, how do we implement the PID equation in a microprocessor? So, that is very simple, that is we do what is known as a discretization. In other words, the integral we simply replace by a sum. So, we say that in a digital controller we can compute inputs at certain instants of time. So, if t is that, those instants of time are called sampling instants. So, at the kth sampling instant, where the time value is equal to k of t, k into t, the input is again consists of 3 terms. There is a proportional value at kt, the integral value at kt, and the derivative value at kT. Now, the question is how do we compute this proportional, integral and derivative terms. So, the proportional controller is simply Pkt is equal to Kp into Ekt. So, we just sample the equation. The integral controller is the integral is actually realized by a what is known as a trapezoidal integration, right, not even trapezoidal, this is you know what is called backward difference integration, right. So, what we are doing is that we simply assume that since Ekt is going to be constant over the time interval k minus 1 to k. So, the integral, so we want to actually what okay. So, what we are doing is that basically we are doing that simple thing that if this is Ekt, this is Ek minus 1 and this is Ek, then after we get Ek, what is going to be the integral, and this is Ek plus 1, that is the error is decreasing like this. So, between Ek and Ek to Ek minus 1, that is between rather Kt to k plus 1 t, I assume that this error is going to be maintained. So, the integral will rise simply as a rectangle. So, I write, so I multiply this integral I realize by multiplying Ekt by t. So, that will be the integral and then I add it with my previous value of the integral to get the present value of the integral. Similarly, the derivative term we make a simple bring this t here. So, then you get this is a basically an approximation of y dot t. So, basically I have to construct approximations of the derivative of y and integrals of y using samples. So, that is what we do, and this implementation form is often called a position form. So, it is called a position form because the whole input u is calculated. Now, as we have seen that in some cases it is rather necessary to generate delta u rather than u, as we have seen, right. So, then now the question is that how do we generate delta u, that is called an incremental realization of the PID controller or sometimes called a velocity form. So, what happens in the velocity form, we need to compute delta u kt. So, delta u kt is very simply computed. Delta u kt is nothing but u kt minus uk minus 1 t. So, we just simply substitute the previous formulae of u kt and uk minus 1 t and then subtract. So, what will happen is that see what happens is the proportional term subtraction give this kp into ekt minus ek minus 1 t. Similarly, the integral term is basically Ikt minus Ik minus 1 t. So, it will give that additional term which I obtained. So, this is the integral part of delta u, and the derivative part of delta u is this, which is basically the difference between this and the same thing at k minus 1. So, basically by taking a difference of these terms you can generate delta u very simply. So, it is not a difficult problem. And then finally, we have to give u, we cannot give to the plant, finally, we have to give u. So, we simply add uk minus delta ukt we have computed. So, we have to simply add uk minus 1 t with that. And there are also some kinds of actuators where let us say like step motors, where the actuator itself integrates the output. So, this summation you need not give, you just keep on giving the delta u's and the actuator will gradually move and will continuously add it. So, in a let us say in a position control using some let us say stepper motor, it is very convenient to give the delta u's. In fact, it is the delta u's which have to be given, and so therefore, the PID control has to be implemented in this form. So, as we have seen that there are some disadvantages of this incremental realization because of the sample realization, and because we in this case we are actually making a second order derivative, not a first order derivative, because there is already a derivative term in u, and we are making another derivative because we want to compute delta u. So, because of sampling approximations, a high amount of noise may be introduced there, that needs to be taken care of. So, your sampling interval should be good, small enough, and the advantages, as we have seen, is that it is very simply possible to give bumpless auto manual transfer, and also for some actuators it is what needs to be given. Now, there is an interesting phenomenon that happens, is that sometimes generally this mode is implemented in this form, there is a PID controller, when there is an integral mode. Basically, because of the fact that if you see the delta u term, you will find that one component contains Ek minus Ek minus 1, that is the proportional component. Now, in this component there is no R, there is the reference input does not appear, because Ek is equal to Rk minus Yk. Similarly, Ek minus 1 is equal to Rk minus 1 minus Yk minus 1. So, if you subtract, and if R is remaining constant, then these will get constant, and you will simply get Yk minus 1 minus Yk. So, and the same thing happens to the D mode. So, in the P and D modes, R does not appear. So, the reference input, so even if even if the output drifts slowly, even if because R does not appear, so it will so the total value of error does not is not reflected in the control input, but in the integral term there is an Ek term, just simple Ek. So, that contains Rk, their Rk is not cancelled. So, it is said that generally when you implement digital controllers in incremental form, you should have an integral mode, otherwise the process may slowly drift from set point without the controller taking corrective action. So, having said that, so that brings us to the end of our lesson. Let us review the lesson once. So, we looked at the P, I and D modes and looked at the various terms, their definitions, proportional band, integral time and derivative time, their meanings, how they can be measured. So, then we saw that these various control modes can give you various kinds of transient and steady state performance. For example, we have seen that the integral control mode can cause integral wind up, it can cause integral wind ups. Similarly, we have seen that the derivative control mode can give you a lot of noisy performance if you have sensor noise. So, some effects of these control modes on performance are discussed. That is, these problems with D and I modes we have discussed, and finally, we have discussed also a digital realization. Now, let us look at some points to ponder, whose answer again, just like earlier lessons, you will find within this presentation itself if you look carefully. So, you might like to write yourself the definition of proportional bands, integral, derivative times. It is, you would like to explain the factors that cause integral wind up. So, integral wind up is basically caused by two factors. So, what are those factors? And we have discussed in this lecture two control architectures which will avoid integral wind up. So, how to avoid that? And then we have seen that while you are implementing derivative control, you have to take care of 2 points such that you do not add unnecessary disturbances and shocks to the plant. So, what are they? And finally, we have seen that a PID controller may be realized in what is known as the position form and a velocity form. So, you need to think how to distinguish between them when which one is required, and also what is the bumpless transfer and how it is achieved. So, the answers to these questions exist in many textbooks and also within this lecture. Thank you very much.